Okay, so today we're going to be doing the first lab. So I didn't send out an email, but we're just going to basically watch a video at some point today where we're going to go over what the lab kind of looks like in person. And then we'll also go through the VKS procedure to kind of get an idea of what we do in the lab. And then after that, we're actually going to do the data reduction. So we'll do one part of it. So now remember that we have 3 different materials for this lab. We have 2 different types of steel and then 1 type of aluminum. So I'll go through kind of one material with you guys, and you'll do the same kind of thing for the other 2. So we're going to be using MATLAB for that part too. So make sure that, well, if you don't have MATLAB installed right now, then it's okay. You can just watch the video, and I'm going to post it to YouTube once it's, done processing today. And yeah, we'll do that. So for this first lab, I'll go over a lot of the data reduction with you. In fact, basically I'll go over like every single step with you, but in the future, I'll go over most of the data reduction with you, and then you will work on, one part by yourself, something like that. And of course, if you have questions for the future labs, you can go on the Discord and ask a question, and I'll help you guys out. Let me share my screen. Okay, so the first thing, well, let's click on the schedule for today. So we have the stress and strain video, which I'm gonna post this, and well, it already is posted, of course, but I'm gonna have you guys watch this on your own, and I'll have you guys basically answer a few questions just so I know that you actually watched the video and kind of have a better idea of what this lab would actually look like. So it'll just be a few questions on, just your understanding, just to make sure that you watch the video. Okay, but before we do that, we're going to go through VKS. So remember, VKS is this kind of online tool that we have to go over the procedure for each lab. So to get to this page, let's go back here. It's on our course homepage. And it's under this link right here, VKS Lab Procedures. So you can go to it if you want, but really I'm going to share my screen, so there's no need to. And if you guys have questions at any point, just put it in the chat. Alright, so Lab 1, stress and strain. So we have 3 different materials. So they're kind of color-coded here, so this one is blue, so it's 1018 steel. If it was red, it would be 1045 steel, and if it was green, it would be aluminum 606 1T6. So all of the different materials that we have, they look similar to this, but just different colors, right? Okay, let's go up here. And I'm gonna open this up again. Okay, so if we were actually doing this lab in person, the first thing that you'd do is measure this gauge length here. So, these parts at the end, when it's a larger cross-sectional area, that's where we'd kind of insert them into the jaws of the machine, which I'll show you in a few slides here. But the first thing you would do is measure this gauge length, and after the test is done and we fit these 2 pieces together, you would measure the length again, and that would be used for the percent elongation that we talked about last time. Okay, another thing we would do is measure the cross-sectional area, or the diameter, to get the cross-sectional area for this gauge length. So in the class, what we do is measure once here, and then once over here, and then take the average. Then we would calculate the cross-sectional area. Okay, so this is the machine that we use for a lot of the labs. I think every lab besides one of them. So this is called an MTS tensile testing machine. Really, I guess MTS Insight tensile testing machine. So again, we use this for pretty much every lab. So these 2 things here, we have this thing right here, and we have this one down here. They are the jaws of the machine. So for this lab, we would insert a specimen to these jaws. So let me go ahead a few slides. So it would look like this. So you see here we put it in the upper jaw, and then we would lower the machine down and then secure on the lower jaw as well. So I'm going to go back. Okay. This little controller here, this is what we use to help control the actual machine here. So we can move the machine up or down, or this top jaw up or down. And this little piece right here is the extensometer. So the extensometer is what we use to measure the strain. And we'll get a better picture of that in a few slides as well. Alright. You know, stuff like this is kind of not relevant for us now since we're not doing it in person. This is the software that we use in the lab. It's called TestWorks 4. And this is the kind of interface that we have here. So once we actually run the experiment, you would see the load that's being applied to the material right here. Crosshead, this is the actual position for the jaws as we go along in the experiment. And then the extensometer reading, that's actually measuring our deformation. Okay, and then of course we would, after we get this data, we would convert our load data and our deformation data into stress and strain, which we're going to do today. Okay, so a little irrelevant for us again for this part. Okay, so here we are securing the specimen to the upper jaw, so we leave a bit of room here when we secure it. Okay, we're tightening it, then we're lowering the upper jaw. We're putting it in the bottom jaw, and then we secure it there. Alright, so this is a better picture of the extensometer that we have. So by default, I think the gauge length here is 2 inches. So for our strain data, we would say that this is our original length of 2 inches. So we would attach this to a material here, like steel. Okay, so this is 2 inches by default, and then these little clips here, they clip on to the actual bar. So we're saying that our default length is 2 inches, or our original length is 2 inches, because this extensometer is going to deform at the exact same rate as the material itself, since because it's attached to the material. So this extensometer, it would, it'd start like this, and then once we start testing, it would, get longer and longer, and that would be measuring the deformation. Okay, so does that part make sense? I want to make sure that everyone's clear on that, because we are going to be using 2 inches as our original length for the once we calculate our strain data today.
Yeah, looks good.
Okay, good. All right. So next thing, this little thing, this is kind of securing our extensometer to be kind of locked into place. So before we actually run the test, we take this little pin out. But again, not totally relevant since we're not doing it. And then we would also want to make sure that these blades here, that they're actually nice and perpendicular to our specimen. So it kind of looks like this top one is a little actually off center, kind of hard to tell, but if we were doing the lab in person, we would want to make sure that these are nice and center on the specimen. Okay, so there it is, fully attached. And again, this pin, it's not taken out yet, but you would take it out right before you actually run the test. Okay, so for a lot of our tests here, we apply a preload just to get everything, started for us so there's no like slack in the machine. Okay, so at this point we remove the safety pin, and then we would start the test. Or we'd zero everything out, and then we would start the test. Okay, let's move on here. So you'd press play, the test would start, and then you would see the load changing, and then the extensometer data changing as well. Oh yeah, also you could actually see a graph in real time of the load data and then the deformation data. Okay, so at this point, the specimen is broken, so it's fractured. So depending on the material, you might see a more defined neck, and for other materials, you don't have much of a neck at all. So if it's a more brittle material, you're not going to have much of a neck here. So you see that the cross-sectional area starts to reduce right here. Alright, this is a better picture of the neck before it fractured. Alright, let's see if there's any other better pictures here. This is just saving the data on the computer. Alright, another picture here. Okay, and then this is aluminum right here for the fracture. Okay, oh yeah, also this picture is good. So one of the other measures that we have for ductility, if you remember from last class, was the percent reduction in cross-sectional area. So remember that we measured the cross-sectional area before we actually ran the test. So once we fractured the material, we would then kind of put both ends together as close as we can, and then we would measure this cross-sectional area right here, the smallest cross-sectional area that we could measure after the test was ran. And then we would use our original cross-sectional area and then the cross-sectional area at fracture, and then we could calculate that percent reduction in cross-sectional area. Okay, so a little bit fast here, I know, but we're also gonna briefly go over this video here. I'll kind of skip through it a bit. But are there any questions that anyone has for this experiment? Okay. Alright, so I'm going to open this up. I have the sound muted, but we'll take a look at this video here. So obviously their machine is a little bit different than ours. It's basically more sophisticated. But the principle behind it is exactly the same. So you see they have a top jaw here and they have a lower jaw here. So they're going to take their material and just, put it on the top jaw and the lower jaw to secure it. So for us, our ends they weren't threaded. So their machine actually has threads on it. And then you see L0 there. L0, this is their gauge length for their test. So gauge length, that just means our basically starting length for the specimen. Alright, so he's going to secure it to each jaw. And you see this thing is actually their extensometer, so it looks totally different than ours. They got a real fancy extensometer here, like a full, huge extensometer kind of machine here. And ours is just a little thing that we attach. So you'll see here, it's going to, this top part of the extensometer is going to go up here. And then, if I remember right, they're going to close in. So their extensometer is this top part here and this lower part here. So, and you'll see that it's lined up to the gauge length that they're using for their experiment. So their gauge length is also much longer than our gauge length for the lab, but the actual length itself doesn't matter because we're going to record that deformation and then we convert it to strain. So the actual length of the material is kind of irrelevant once we convert it to strain. Okay, so I think they're going to begin the test here. And there you go. So you can see that they're recording the force data along this axis and then the elongation or the deformation data along this axis here. All right. Go back a little. So here we are totally linear here, so we're in the elastic range. So if they were going to unload this data rate or unload this material here, completely take the load off, all of that strain would be recovered. And then if we keep playing. It's about to yield right there. So at this point, it's yielding. So if we were going to unload this now we can't recover all of that strain that was just applied to this material. Again, that's you can see that because we're not in this linear range anymore. Also, you see that now, let's actually play it a little bit more. We have no increase in load here after this point, but we have a very large increase in strain. So that's another indication that we're yielding. And for this material, we have an upper yield point, which is up here, and then we have a lower yield point, which would be like down here. So not all materials are going to have 2 yield points, but some of them, like this one, will. So you'll see for aluminum, that's actually going to be a case where there isn't a defined yield point. In that case, we're going to use our 0.02% offset method that we discussed last class. Okay, so we'll keep playing it. So it's going to keep yielding here, and then eventually it's going to go through the strain hardening phase, where the load will start to increase again. So it's a pretty long yielding phase for this material. I think it was some type of steel, if I remember correctly. Okay, so now we are going to strain harden here. And then we're going down. So we're necking. So look how much it's necking over here. I'm going to go back a little bit. So because this material that they have is so large, you can really see it neck. So I'll play it again and keep an eye right there. Yeah, this is pretty cool. It's deforming way more than you would see in our lab. So pretty pronounced neck there, and it's going to fracture very soon. Alright, and there it goes. Okay. And then I'm going to show you another one that they test. Okay, so here's the upper yield point, and then here's the lower yield point. And then F max, that's going to be our ultimate tensile stress, or ultimate tensile strength. Okay, let's go through here. They're using different symbols than we use, but I think they're from somewhere else, so I guess they use a different kind of convention for that. Okay. Oh yeah, so you see here, they're showing you the same exact material, obviously a different one. Basically, kind of giving you an idea of the before and after. So here is what the material looked like in the beginning, and here is what it looks like after. So it elongates quite a lot, and you'll see that the necking here is also very pronounced. Okay, so this next material, it's not going to have a defined yield point. So we go through here, you see it's already starting to yield here, but that yield point isn't defined like the last material. So in this case, we would use the 0.02% offset method. Okay, so it's, yeah, okay, the neck is starting now. Okay, when it fractured here, so you could hardly see necking occur in this material. You can, if this was a better resolution, you could see it a bit, but this material is more brittle than the last material, so there's not much necking that's going on. Okay, if we go through here, oh yeah, so they're actually showing it the 0.2% offset method here. So that's what we're going to be using for our lab. Okay, any questions on this video? Okay, so I know it's like a huge step down from actually doing a lab in person, but this is kind of the best thing that we can do now. Is just watch a video and kind of get an idea of what is actually going to occur in the lab. Okay. So if there's no questions, then at this point we're actually going to get started with the data reduction for the lab. Okay. So if you have MATLAB, you can open up MATLAB right now and kind of follow along with me. So again, I'm going to go over just one material, but the other two materials you do the same exact kind of method. Okay. I'm getting this set up here. I'm going to reference basically the script that I already wrote, so I'm kind of finding a good spot to put it. Okay. Let me put this down here. Okay, I'm going to share my screen again. Alright, so this is already the script that I wrote, so I'm going to clear this out. Let me change my color. Did we talk about how to have dark mode in this class, or no? I think maybe not.
Nah, that's pretty cool though.
Okay. This will be very quick, so if you don't care about dark mode, don't worry, it'll be quick. But if you guys want that kind of dark mode that I had, MATLAB doesn't have like a built-in dark mode feature. Who knows why? It's now 2021 and they still don't have that. But if you want it, you can click on add-ons up top here. And then you're going to download an add-on that's called MATLAB Schemer. So if you type in Schemer, you can click this first link here. It's by Scott Lowe. And then you would see like an install option right here. So you could click on install, and then basically you would click on open folder, and you'll see your folder pop up here on the left for this add-on. And then let's see, yeah, you're gonna click on this folder here, which says Scott C. Lowe, MATLAB Schemer. And go to schemes, and then you can see all of the schemes that they have in here or that are, installed on the add-on. So it's all of these besides Dracula. So I installed that myself somewhere else. And then if you want to use a theme, you would do schemer import, and then you would say whatever theme that you want to use. So like Dracula.prf, and then you'd press enter, and then it would go. So if you want to do that, that's how you would do it. So it's pretty good, because if you're using MATLAB at night, you don't want to have your retinas, get destroyed. So if you want to do that, you can look at this video, back after. Alright, so let's go back to my correct directory here. Alright. Okay, so what I'm going to first do is make a new script. So that's what we're going to be using for all of our data reduction. So to make a new script, I think everyone's taken 205, right?
I think so.
Okay. You should. I double checked the flowchart last night, and 205 is like
That's
I think like a year before.
right, Professor?
Yeah.
Yeah.
Okay. Alright, so you guys should be familiar with this. Maybe it's better now, but I know at least when I took the class, basically everyone didn't feel confident in it even after they took the class. So maybe some of this will be, hopefully it's just a refresher, but I don't know. Anyways, we're gonna make a new script. So all I did, I'm on the home tab here and I click on new script over here. And then we see that we're in the editor window, which is what we're gonna use to make a new script. Okay, so the first thing we're going to do is make a few comments here just so we can reference this or get an idea of what our script is if we're looking at it later on. So I'll just say data reduction, experiment 1, and then stress and strain. Okay, after this we're going to clear the memory. So this line here that says the word clear, that's going to clear everything that's stored in our workspace over here. So basically if I had some variable over here like x equals 2 and I didn't really want that for my script, this line of code is going to clear that out of the workspace. And then CLC, that's going to clear any text that is in the command window down here. Okay. So let me save this right now. So I'll go to save as. And when you save a file, if you save a script file, you can't have any spaces in it and then name, and you also can't start it with a number. So if I did like 0, 1 and then whatever, you would get an error. So we need to start with a letter and we can't have any spaces. So I'll do experiment 1, stress strain, and class. Okay, so if I run my script, you're going to see that the workspace over here is going to get cleared out. I'll run it and it goes away. So I'm not going to spend too much time on the basics of MATLAB because, again, all of you should have taken MATLAB before. So it should be a refresher. Okay, so I'm going to make a section here and I'll call this define knowns. Let me change that background color. Okay, so in this section, we're going to define the knowns for the lab. So I'm going to give you guys a data sheet. It should be today. So I was looking at a past lab that I taught for this class. And my students, at least in their Excel document, they only had the cross-sectional area in the beginning. So I also need to give you guys data for the cross-sectional area at the end. So I'm going to get a new, basically, some new Excel sheets, and I'll upload that sometime today, and then you guys can work on the lab. So the data that I'm using right now is going to be different than the data that you guys have, but the workflow is going to be the same. So first thing, to find knowns. So actually, before we do this, we're going to import our data. So let me do import data. Okay, so I'm going to call this S_1018, just standing for steel 1018. And then we're going to use a function called read table. So this is going to use, or we're going to have a table once we use this function. But you could also use something like read matrix if you want as well. I'm going to use a table in this case, just because that's what I did yesterday. But using a table can be beneficial because a table in MATLAB can store different data types. So for us, it's actually not really needed, just because all of the data that we have over here, they're just numbers. But if we had something like string data in here as well, that would be useful. But just since I used a table last night, I'm going to use this function again. Okay, so I'm going to say read table, and then we're going to put the file name that we are going to import. So for me, this is Throckmorton. I was a past student. Blue experiment1.txt. Okay, so this is the file name that you can see over here on the left. And then I'm going to put variable naming rule preserve. So this is just going to make sure, or it's going to ensure that we don't have any warning signs. So I'm going to copy and paste this just to show you why I'm doing that. comment that first one out and delete all of this. So if I run our script right now, you see on the bottom here we have a little warning. So that's for our column header. So if I open up our table, it actually looks correct here, but the warning is just annoying to look at. So I'm just going to say variable naming rule preserve, and basically what that is doing is it's ensuring that these names up here like load, time, and crosshead and extensometer are preserved. So I'll delete this line again. And now if I run it and I look at the table, you see the table is the same, but I don't have a warning message anymore. Okay, so we have these 4 different columns. So we have load, which is in pounds, time in seconds, crosshead position in inches, and then we have the extensometer, which is in inches. So this column here, extensometer, that's our deformation data. So all we're going to use is the load data and the extensometer data. Alright, so that's how we're going to import stuff. Again, you can use a different method if you want, but this is what I'm going to use for this kind of workflow with the class. Okay, so now we can define our knowns. So again, I'm only going to do it for one material, so I'm only importing 1018 steel, but I would do the same kind of thing if I was importing the data for 1045 steel and then aluminum. Okay, so defining our knowns, we have the cross-sectional area. So this is something that I will give to you. So for this lab, steel 1018 had a cross-sectional area of 0.0908, and this is inches squared. So I'm gonna put a little comment just so I know what the units are. Okay, and then I'll define the gauge length here. So I'll say gauge equals 2. So remember, the gauge length is the our initial length for this test. So we use the extensometer, which has a gauge length of 2 inches, and that's going to deform at the same rate as the material itself. So we're gonna use an original length of 2 inches. So I'll say gauge equals 2, that's 2 inches, and then I'll put a comment as well. Right. I'm gonna move this over a bit just because I'm referencing my script I wrote. I know you guys can't see the script that I'm looking at, but I actually have my script open up right here where my mouse is, but I'm not showing that part. Okay, so if we run our script right now and we look at steel 1018, let's look at this table here. If we scroll all the way to the bottom, we see that there's a sudden drop off in the load. So that's, we fracture right here, and then the graph would basically go like straight down. We actually saw that in our video. So at this point, we fracture right there, so I don't need to see this last part. So we're actually going to delete this entire row. And this will make more sense once we actually make the graph. I'll show you what it looks like with this row in here and then without. But since we don't need that row, we're going to delete that.
Professor?
Mm-hmm.
I wasn't able to see the table that you were referring to.
Oh, yeah. Yeah,
So,
okay.
Sorry.
No, that's fine. I forgot I was only sharing this MATLAB window. Okay, let me stop sharing. I'll share it again. Okay, so I'll just share it like this. So this is my script there. Okay, so I'm going to open up the table. Now you guys should be able to see it. So if I go to the bottom, so you see right here, there's a sudden drop off in the value for the load. Everyone can see that, right?
Yeah.
Okay. So it already fractured in row 667. Close on there. Not 666. Okay, so there's a sudden drop off in this row here. So we actually don't need this value here. And I'll show you guys what it looks like again once we actually plot the data. So what we're going to do is remove this last row. So we're going to do this in a way where I don't need to know the actual number for that last row. So I'm going to make a little comment here for taking out the last value. So I'm going to do s underscore 1018. And then I'm going to say end. So this function here, end, that means the last value that's in our vector, or in our table, I should say, for this. So if I go to the very bottom, it's going to reference this last row. Let me tuck this aside. Then I'm going to put a comma and then a colon. So this is saying to take our last row, which is end, and then the comma and the colon, that's going to reference all of the columns. So we always do row, comma, column. So the row is end, and then we take all of the columns. The colon operator means everything. So in this case, it means all of the columns. And then to delete it, to delete that entire row, we're going to use empty brackets. So hopefully this is review again, but if you guys forget, that's kind of the explanation. So if I run our script, you'll see this last row here is going to get deleted. So I'm going to run it, and then it is deleted. Right? Okay, so now we're ready to calculate the stress and strain. So I'll make another section, calculate stress and strain. So I'm going to call this s underscore 1018, and then I'm going to do dot stress. So this syntax here is going to create a whole new column for us in our table. So if I open up our table again, you see that right now we have 4 columns here. Okay. I'll put that down here. So if I do s underscore 1018, that's referencing our table, which is called s underscore 1018. And then when I put dot stress, that's going to tell MATLAB to make a whole new column that's called stress. Okay, now I'm going to use a function called table to array. So right now, our table is, well, a table. But if I'm going to do a calculation on our table, I need to convert it into a number. In this case, it's really a double, which is a type of number for MATLAB. So we have to convert it from a class of table to a number. So I'll show you why in a second here. So just use this function right now, and then we'll show you why we have to use it. Okay, so table to array. And so we're going to calculate stress here. So we're going to take all of our load data and then divide that by our cross-sectional area. So for every row here, I need to take the load data and then divide it by the cross-sectional area that we defined on line 10. Okay, so I'll do table to array. Then we're going to reference our table, which is s underscore 1018. And in this case, I'm going to take all of the values in the first column. So remember, it's rows, comma, columns. So I want every single row. So I'm going to get all of these values. And I only want to look at the first column. So I put comma and then 1. So that's going to be this first column here. It's going to take all of these values. Okay, so we have the load data, and now we need to divide this by the cross-sectional area. Okay, so I'm going to do divided by s underscore 1018 underscore area. Okay, so if I run this now, it's going to run okay. But I'll show you why we need to do table to array. So I'm going to copy and paste this, comment this line out. If I didn't have our function table to array, and I try to run it, you see that we have an error here saying that we can't actually divide this because our class for our table, it's actually not a number. So if I do class underscore 1018, and we'll even be specific here. We'll say for this first column, it says it's a type table. So MATLAB sees that every value in our table here in this first column, we see that it's a number, but technically MATLAB sees that it's a table. So we're trying to take a table and divide that by a number. We can't do that, of course. We need a number divided by a number. So we have to use our function table to array, which will convert this from a type or a class of table to a number. So let's run this again. And now if I look at this class and I do table to array, now it says it's a double, which again, that just means it's a number. All right, so hopefully that made sense. I don't want to get, too, I guess, long-winded for these technicalities here, because again, this should be a review. But if you guys have questions, of course, feel free to ask.
So I have a question.
Mm-hmm.
Where are we getting that table from?
Yeah, so I didn't upload it yet, but this table was basically imported. So, up here we use the read table function, and that then makes this table right here called s underscore 1018. So this comes from this file over here on the left.
Okay, and then we'll have access to that file later?
I'm going to give you different data, but yeah, I'm going to upload that data to Canvas sometime today.
Thank you.
Mm-hmm. Okay, so let's look at our table again here, and now you're going to see that we have a new column that's called stress. Go back over here. So I'm going to comment out this line just to show you what we did. So if I run this, you see that went away. Let me run the script again, and then we're going to get a new column that shows up here that's called stress. And there we go. So our stress here, that's going to be in units of PSI, or pounds per square inch. Okay, so there's stress. Now we need to calculate strain. So we're going to basically append a whole new column for this as well. So I'll do 10 underscore 1018 dot strain. Oh yeah, I just realized, yeah, I was telling you guys that you could follow along, but you can't follow along because I didn't give you this data. So, I guess you just have to watch me here, so sorry about that. But I want to give you different data just so I know that you guys actually worked on it yourself too. Okay, so we're gonna do.
So I'm trying to. Quick question. I'm so sorry. So I'm trying to follow along, without the data, and just like put placeholders where I'm going to be putting like the other, the other steel and then the aluminum. But the gauge is going to be 2 for all of them, correct?
Yeah, that's correct. Yeah. Yeah,
Okay,
it'll be
thank you.
2 inches because we're saying that the gauge length is the original length of the extensometer, which is always 2 inches. Okay, so we're going to calculate strain now. So we're going to take our data once again here. Okay, I'm looking at my code here. Okay, yeah, it's fine. Okay, so we're going to do table to array. Just like before, we need to convert our table to basically a number. And I'm going to take the deformation data that we have. So that's going to reference our table, which is s underscore 1018. And then I want to get all of the values in column 4. So that's our extensometer column, which is just the deformation data that we have. And that's in inches. So this is basically delta L. It's our change in length. Okay, so we're going to say I want to get all of the rows in the 4th column. And then we're going to divide this by the gauge length. So we defined gauge, which is 2 inches. So that's all we have to do. And now if I run this code, then you will see that we're going to have a new column here in column 6. So let's run this. And there we go. Now we have our strain. So this is in units of inch per inch. Let's actually put our units here. So I'm going to make a comment. We have pound force per inch squared. And then for strain, we have inch per inch. Alright, so now we have our calculation, so now we can actually move on to the plotting. So I'll make another section down here for plots. Actually, I'll do it like this. I'll say 1018 steel plot. Alright. Okay, so I'm going to use a command called figure. So I'm going to say figure, and then visible, and then on. So as we go along with our script, once we keep running it, typically what we have, like something you might have learned when you took EGME 205, you probably used a command like figure and then 1. So that's pretty standard, and you can of course use this command as well. And basically this tells MATLAB that this current figure that I'm going to make is going to be called figure 1. And then if you had code, after this for a whole new plot, you would call that something like figure 2. So you can generate both figures. If we didn't have this command and we wanted to make 2 plots, then MATLAB would keep overwriting each figure as it goes along in your script. So if we want to actually generate each plot, we need to tell MATLAB, okay, this is figure 1, and this is figure 2, this is figure 3, and so on. But what I'm going to use in this kind of lecture here is figure and then visible on. So this will still save each figure that we have, but I can tell MATLAB whether I actually want the figure to pop up or not. So I can change this to visible off if I want to run my script but not have my figures pop up. So I use this because a lot of the time we actually don't want the figure to pop up when we're, doing something else in our script. But this line is optional. So this is going to access the strain column in our table. Now we have to specify the y data, so that'll be s_1018.stress. And this is all we need. So if I run this right now, oh, that was just a warning sign. So this warning sign is just for my system. And it's just a warning. It's just a warning for graphics, basically. So let's go back here and run this. And here's our figure. So I'm going to add an X label and a Y label, and we're going to, make this look a bit better. But here we have stress on the left, and then on the X axis we have our strain. So you see here is the elastic range, and there's not a defined yield point here. It's a pretty, relatively speaking, it's not gradual. It happens pretty fast. But if we zoom in on here, we can't really see a defined yield point. So we're going to use the 0.2% offset method. And then see over here, this is when we fracture. So I'm going to have that go again. And there we go. This is the plot. So now we're going to do a few more things to make the plot look a bit better. So first thing, let's do our X label and our Y label. Actually, I'm also going to change a few things for the actual, how the actual plot looks. So first I'll do a comma, and then in apostrophes in R, and this will specify the line color that we have. So it's going to be red. And I'm also going to make the line width thicker. I always think the default line width is too thin on MATLAB, so I always put it to either 1.5 or 2. So if I run this now we have a red plot, and the line is thicker as well. Okay, now we can add our X label and our Y label. So our X label is going to be strain, and this will be inch per inch. And then our Y label, that's going to be stress. So we'll do Y label, stress, and that'll be in pound force per inches squared. So if we're in this now, we have our X label and our Y label. Okay, optional part that I'm about to show you, but I personally recommend it. It looks a bit better. So if I run this again and we look at our graph here, you know, the way I wrote pound force per inches squared, this isn't really recommended because, you know, I should have an exponent for inches squared. And as it currently is, I don't. And, you know, some people will put a little caret sign there to, you know, to stand for inches squared, and that actually does put inches squared up like this, so that's good. But what I would really prefer to see is an actual fraction. So to put in a fraction in MATLAB, there might be a different way, but I'm going to put in LaTeX code. So if you guys aren't familiar with LaTeX, it's basically a text editor, and you can write LaTeX code in MATLAB, and MATLAB will be able to read it as LaTeX code. So again, this part is optional really. If you run it like this and you submitted this in your memo, I would accept it. It's okay, but for me personally, I like to make it look a little bit better. So I'll show you what to do. So again, you can leave it like it currently is, and that's fine. But what I'll do instead is I'll have strain, and then I'm going to put a $sign, $2. So right now, this is going to stand for basically typing in a math equation in LaTeX. So we have $2 signs. I'm going to put a backslash left, and then a parenthesis sign. This is going to make a parentheses, and then backslash frac. So now we're going to define a fraction, and then in our curly braces, that's when we put in our numerator and then the denominator. So we have we're in the X label, so we have inches and then inches. So this is the numerator and this is the denominator. And then we're going to do backslash right and then put our right parenthesis. And over here we tell MATLAB that we are basically writing LaTeX code. So we're going to put interpreter and then LaTeX. Okay, now if I run our code again, now you see on the x-axis we have strain and then inches per inch, and this is interpreted as LaTeX code. So I want to say again, this part is totally optional. You don't need to do this, but I think it looks a bit better, so I'm going to use it myself. Okay, now we have to do it for stress, so I'm going to put backslash left, fraction, we have pound force per inches squared. I'll do backslash right, and then interpreter LaTeX. Okay, and then again you can see that now we have pound force per inches squared. I would maybe actually make this a bit bigger for the LaTeX text, but I'm not going to go over that now just because I don't want to get too bogged down for that. Okay, so we have our X label, Y label. One last thing we're going to do is change this up here. So right now, our units for stress, we have 10, well, you know, whatever number, and then times 10 to the fourth. So that's a little harder to read, you know, in my opinion, especially how it's kind of tucked up here. So we're going to change this so we don't have this displayed as an exponent up top here. So to do this in MATLAB, we have to do AX equals GCA, which is basically a command that stands for get current axis, and that gets all of the properties for whatever axis that, or whatever axes we have for our figure. Okay, so GCA, it's going to get all of the properties for the axes on this figure that we're currently making. And then I'll do ax.y-axis.exponent equals 0. So you need to make sure that your capitalization is the same that I have here. And this is now telling MATLAB to look at the axis, so ax, and then we put dot y-axis, so look at the y-axis, and then we say dot exponent, so we want to modify the property for exponents, and then we have that equal to 0 because we don't want an exponent. Now if we run the script, then we don't have exponents that show up anymore for stress. Okay, so there we go. You can also put in a title here if you want, but I would actually recommend just using a figure caption in your memo. So it's redundant to put a title in your figure and then also have a caption. So do either or. Personally, I recommend to just put a caption for your figure, which would be under the figure. But if you want a title, you can just put in title. And this is 1018 steel. So I'll say stress and strain for 1018 steel. Now if we run this, then there's the title. Okay, do we have any questions? We have a few more things to do. So we need to find the elastic modulus, and then we're going to use our 0.2% offset method. But before we do that, are there any questions? Okay. Does everyone remember all of these MATLAB functions so far? I know it's kind of like, it's a lot of stuff to remember if you haven't used MATLAB in a while. Okay. Okay, so now we're going to calculate the elastic modulus. Oh, I also didn't mention earlier, I should have. I'll be uploading, or already did upload the deliverables for this lab. So to look at them, you can click on assignments. So I've put in an assignment for when this lab memo is going to be due. So it's going to be due on February 22nd by 11:59 p.m. So starting from today, you have 2 weeks to work on it. So if you click on this, you can then see the deliverables that I have. So we'll click on that. And this will tell you everything that you have to do for this memo. Okay, so it looks like a lot, but we're actually doing a lot of this right now. So you need to compute the stress and strain for each material. So, we're doing that for 1018 steel right now. And then you're going to plot the stress strain curve over the elastic range and then the entire range. So what we're going over in class is plotting it over the entire range, but you can modify your code to only, plot a certain amount of rows basically for the stress and strain that you've calculated. And then you can have it more zoomed in on the elastic range. So for this part here, I'm not going to be super strict on it because we're using the offset method. Basically, I just want you to kind of zoom in on or restrict the, the range that you have to just look at the elastic range. And I'll actually kind of show you what I mean also. Actually, I'll do that right now after I talk about this. Okay, so we're going to have 2 graphs per specimen. So right now we're doing 1018 steel, so we should have a graph for the entire range, and then a graph for the elastic range. Okay, then we have to label some parts on our graph. I'll show you how to do that as well. And then the section here for error analysis, we're going to calculate the elastic modulus and compare that to a published value. The yield strength, so that's when we're using our offset method, and we'll compare that to a published value. And then the ultimate tensile strength as well. Okay, then you're going to calculate the percent error, and then the last thing we have to calculate is the percent reduction in cross-sectional area. Okay, so also a little reminder, which we're also going to go over, you need the mapping toolbox to find the intersection point for curves. So this is what we are going to be using to find the yield strength, which we're about to go over. And then simple calculations at the end of your report, you need to have a few of them. So you need to have simple calcs for stress, for strain, the elastic modulus, and then the percent reduction in cross-sectional area. So for that, I should see your figure in symbolic form, kind of like you see here for the elastic modulus, and then you should show one sample calculation per per thing here. So one for stress, one for strain, and then like one for the elastic modulus. So you would plug in values and then calculate that. Okay, so let's go back to MATLAB. So if we're going to plot this for the elastic range, just looking at this graph right now, I know, and we want to actually show the yield point as well, or the yield strength. So just looking at this graph, I can see that maybe I want to go to 0.02 inches per inch. So that'd be, right here. So to restrict our graph to only go to there, I can use a command called xlim. So xlim stands for x limit. And then I'm going to put in 0.02. Do I need brackets here? I forget. Yeah, I guess I do. So, oh yeah, I remember now. So we're going to go from 0 to 0.02. That should work now. Yeah. Okay, so xlim takes 2 arguments. So in brackets, we have to specify where we start. So that'll be 0. And then where we want to end. So that'll be, in this case, 0.02 inches per inch. And once I run this, you see that our graph is now restricted to go to a maximum of 0.02 inches per inch. Okay, so that's how you can do that. For now, I'm going to comment this out. And now let's calculate the elastic modulus. So we just saw the formula for that. We're going to do sigma 2 minus sigma 1 over epsilon 2 minus epsilon 1. So we're taking 2 values for stress and then 2 values for strain. And also just to, kind of have some emphasis on it, this is of course just doing, rise over run. So all we're doing is finding the slope in the elastic range, which is of course the elastic modulus. Okay, so let's have a new section here, elastic modulus. So I'll call this S underscore 1018 underscore capital E, so elastic modulus for 1018 steel. And then we're going to use our function table to array once again, because we want to use or convert a table to a number basically. So we'll do table to array. So now we're going to reference the values that we want to look at in our table. So I'm going to do S underscore 1018. And here I'm actually going to specify the actual row that I want to look at. So there are different methods that you can use, but just for simplicity, because we would be writing even more code, I'm actually just going to manually look at our table. So if you have more experience with MATLAB, you can do it a different way. Again, you can basically, let me run our script here. So if you're, again, more experienced with MATLAB, you can basically do this where you can say, take the first value that's greater than or equal to 8,000, let's say. So to calculate the elastic modulus, we just need 2 points for the stress and 2 points for the strain. So it doesn't really matter. You just need to be within the elastic range. And ideally we want to take a point or 2 points that are spread apart. So somewhere down here will be 1 point, and then somewhere up here for the other point. Because if we take 2 points that are very close to each other, like let's say right here and here, there's some kind of inaccuracy with the machine, you'll see it's actually kind of jagged. Let's zoom in here. It might still be hard to see, but it's not a totally smooth line. So if we take just, this point and this point, there's some kind of variability there. So by taking 2 points that are really far apart, we can kind of get a better average to find our elastic modulus. So to do that, we want to take a point that's down near the origin and then a point that's towards the top of the elastic range. Now, the yield point here isn't clearly defined, but we want to make sure that we're not going in a point where it starts to curve up here. So basically, I know I'm kind of going on a tangent now, but you could write code to say take the first value that's after, let's say, 70,000 psi, and then we would take that as a point. But that's just going to complicate things, so what I'm going to do right now is just look ourselves in our table here to get a value that we want to use for the elastic modulus. So last night it looks like I looked at row 272, and that was a value for our stress of 8.8 times 10 to the fourth. So let's look at our plot again. Let's make sure it's actually a good number. So that was around 90,000. That looks bad, actually. Let me make sure I'm looking at the right thing here. S1018. Yeah, that's blue. Okay. So I'll actually do a different value here, because around 90,000 looks like a bad number to use. So let's use the value around 70,000 right here, because we can tell that we're still linear once we get to 70,000. Okay, so let's look at when 70,000 is reached. So we see that's row 200 here. So I'm going to take row 200 as one of the points that we're going to use for stress and for strain. So let's change this to 200. Okay, so this is our first point that we have. So this is basically sigma 2. And then we want to do minus sigma 1. So in this case, I just said, let's take the 15th row. So if we go back to our table, the 15th row, that corresponds to a stress of 5,000. So that's fine. We can even go a little bit lower. Let's do, what was row 10? Row 10, it's around 4,000. So we'll do row 10. So I'm going to do S underscore 1018. I have to do table to array once again. So do table to array, and then S underscore 1018. Then I want to look at row 10, and then we need to take column 5. So we're looking at the stress column. Let me pull this out a little bit more. Put that over here. I want to make sure that we can see this on one line. Okay, so this is our numerator up top here. So we have sigma 2 right here, and then we have sigma 1 over here. Okay, now we put our divide sign, our division sign, because we want to put it in the denominator. And then these 3 dots, they basically just allow us to go to the next line. And those 2 lines are going to be interpreted in MATLAB as one line of code. So I'm putting in these dots here just so this is a kind of cleaner to read. Okay, so I'll put divided by, and now we're going to put in our denominator, so table to array. Then I'll do S underscore 1018 to reference our table. And then I'm going to use row 200. And now we're putting in basically epsilon 2. So that's our strain. So because it's the second point, we're using row 200, just like we used here for stress. And then I have a 6 here because that stands stands for the sixth column for string. So we have column 6. Alright, and then we have minus table to array, s underscore 1018, and then we're going to put in 10, comma 6. This is epsilon 1. Okay, so there we go. This should now calculate our elastic modulus. Looks like I'm missing a parenthesis sign somewhere. Right here. Yeah, okay. So there we go. So now we calculated the elastic modulus for 1018 steel. Alright, and you can see the value right there. Okay, so we're almost done. I know it's, kind of tedious, I guess. Okay, so there's the elastic modulus. Are there any questions on that? Okay, so now we're gonna do the 0.2% offset method. So I'll make another section here, 0.2% offset method. So in the deliverables, you saw that I had a note, which is that we need to use the mapping toolbox to find the intersection point for curves. So that'll be when we basically draw our line for the offset method. Let's go to Google Images. So I'm going to do 0.2% offset method. Okay, so, we draw this line parallel to the slope, which, is going to be our elastic range, or elastic modulus, sorry. And to find this intersection point here, which is going to be our yield strength, in MATLAB we need a toolbox that's called mapping toolbox. So by default, it's not going to be installed. Maybe you installed it, but probably not. So to install that, you need to go to add-ons again. And then we'll search for mapping, press enter. And here we go. This is the mapping toolbox. So once you click on that, you should have a button around here that says install. I already have it installed, but you can install that and then you'll be good to go to find the intersection point for two curves. All right, so let's do this now. Okay, so the first thing that we're going to do is calculate the x values and the y values that we have for this line that we're generating for this offset method. So what we're doing is finding all of these corresponding x and y values for this line here. Okay, so the first thing that I'm going to do is define the x values for our offset method. So I'll do s underscore 1018 underscore off x. So that just means offset and then the x values. So here I'm going to generate basically an x range. So we want to start at 0.002. So that stands for 0.002 inches per inch, or 0.2%. And then I'm going to use a step size of 0.001. And then we're going to have our last value be 0.006. So basically, if we look at our graph here, I'm basically just doing a range from 0.002, so somewhere over here. Let's zoom in actually, why not? So we're going from 0.002 to 0.006. We're going from right here to right here. I'm doing that because once we actually make this, use this offset method, we don't need to go way out over here. So it'll make more sense once we actually make our plot. Okay, so now we need the corresponding y value. So I'll do s underscore 1018 underscore off y. And now we're going to actually, get all of those y values that we want to have for this offset method. So we're gonna look at the elastic modulus. So that's S underscore 1018 underscore E. That's what we calculated right here. And then we're going to multiply this by our X values that we just defined right here. So S underscore 1018 underscore off X. And then minus 0.002. Okay, and there's a question, will I be posting this recorded lecture? Yeah, I'm going to post it as soon as it's done processing on YouTube. Yeah, I know there's kind of a lot of stuff here. Okay, so what this line of code is going to do, it's going to offset our line by 0.002 inches per inch. And then it's going to take our slope that we have for the elastic modulus, right? Because that's the line that we want to plot. And then it's going to basically generate all of these corresponding y values. So let's run that. That's fine. And then now I'll actually show you what this looks like on our plot up here. So I'm going to actually take all of this. I'm going to move this below. Put it here. So now I'm going to use a function in MATLAB that's called hold on. And that allows us to have multiple plots or curves on the same figure. So now I'll do plot S underscore 1018 underscore off X, and then S underscore 1018 off Y. Those are the two X values and Y values that we just defined for the offset method. Then I'll do hold off. Let's run this, and there you go. So this is the offset method. So at this point, right there, where these two curves intersect, that's our yield strength. So that's what we need to find, that intersection point. Okay, so we need to find that, and that'll be the yield strength that we're going to use. Because again, this yield point that we have in here isn't clearly defined. Because of that, we're using this offset method. Okay, so this is when we need to use that mapping toolbox that I just talked about. So I'll make a comment, make a section. So I'll say find, find intersection points, or point. Okay, so to do this, I'm going to put S underscore 1018. Of course, you can use whatever variables you want to use. Use something that makes sense to you. So I'll do S underscore 1018 for 1018 steel, underscore off for offset, and then underscore XI standing for kind of intersection point. Okay, so this will be the X value for the intersection point, and then I need to put S underscore 1018 underscore off YI, and that will stand for the Y value for the intersection point. Now we're going to use a function called polyx, and then poly. So this is, when we use this function, this is when we need that mapping toolbox that we just talked about. And in here, we're going to define the two curves that we're referencing to find that intersection point. So first off, I'll do S underscore 1018 or dot strain. So, you know, this is taking all of the strain data for our entire plot, for the stress strain plot. Okay, I'll type all of this out, and then I'll kind of break down the code a little bit more. Okay, so we have our strain data, then we need to put our stress data. So 1018 dot stress. And then I'm going to put S underscore 1018 underscore off X, S underscore 1018 underscore off Y. Okay, so I know this is a lot, so let's kind of break this down again. So first things over here, in brackets, we need to define the variables that we're creating for our intersection point. So what I have highlighted here, this variable is going to be created, and this will be the X value for the intersection point that we're finding for that yield strength. This, what I have highlighted now, is going to be a variable that's created for the Y value for that intersection point. to find the intersection point, we need to use this function called polyx, poly. And remember, for this function, we need the mapping toolbox. So this function will find the intersection point for two curves that we specify. So the first thing here, we have s underscore 18.strain, and then we have s underscore 1018.stress. So that corresponds to, let's make this a different color. I'll make it blue. Okay, so let's go like this. S underscore 1018.strain and S underscore 1018.stress. It corresponds to this curve in red, which is, our stress strain data that we created for 1018 steel. Okay? And then we need to specify the other curve. So the other curve is going to be this blue curve that we made for offset method. And that corresponds to the x values that we created, and then all of the y values that we created to make this blue line. Right? And then so we ran our code, and then we get our values over here. So let's do this. So this is going to be the x value for that intercept point, and this will be the y value for that intercept point. So this y value, this is going to be the yield strength that we have. So it's at 95,000. Let's look at our graph again. So it's 95,000, and just looking at this, kind of eyeballing it, that seems about right. We can even confirm this. Let me take these two lines here. And then I'll put this up here. So let's confirm that this intersection point is actually correct. So I'm basically going to plot a line for that yield strength. So I'm going to do y line. This will make just a horizontal line. So I'll do y line and then s underscore 1018 underscore off underscore yi. So that stands for the y value for that intersection point. And I'll make this a dashed line. And there it is. So it's right there, right? That's our intersection point. And this, so remember, this black dashed line stands for the value of our yield strength. Okay. Let's see if we got anything else. I don't think so. Alright, so yeah, that's it. I know that was a lot, especially if you haven't used MATLAB in a while. I know it was probably a lot to kind of remember. But using MATLAB, especially for the next lab that you take, 306B, is going to be very, very useful. So everything that we did here, we could do in Excel, but you're going to be using MATLAB in a lot of your classes throughout undergrad. So I think it's valuable to use it. And I'm going over this with all of you because I know, at least when I took MATLAB and I had to use it for some classes, it was hard to kind of work through on my own. So I want to go over all of this with you guys so you can kind of get refreshed in hopefully a better manner than just trying to work on it by yourself. So is there any questions for what we went over today?
I have a question. Does it matter if you move like the whole section, like because you move the plot from like when it was between the calculating the elastic mileages? Does it matter if you move it down or leave it up there?
Yeah, so you can move stuff. You just need to make sure that, here I have the plot as the last part now. You need to make sure that everything that you have for this code was already defined before it.
Okay.
Because MATLAB, when you run the script, it runs it by going top to bottom, by kind of line by line.
Okay, thank you.
All right. Any other questions?
Yeah, just a really quick question. So we don't have class next week because of President's Day, and then it's due the next week after that, correct?
Yeah.
Okay.
Thanks for reminding me about that too, because I forgot that. Next week we don't have class because of President's Day. Yeah. And then also I'll be posting the different data than what I showed you guys in class. I'll be posting that sometime today. I just need to make sure that whatever data that I give you, I also have the cross-sectional area at fracture. So I'll post that sometime today, and then I'll send out an email when that's posted too. Alright, if there is no other questions, then that's all I have for you guys today, so I will see you in 2 weeks from now.
Thank you.
Thank you,
Bye.
Professor.
Mm-hmm.
Thank you.
Thanks.
Yep, see you guys.